Alright, so I want to make another quick video on having a physical VR body. So, especially if you're following a lot of tutorials, you're going to run into a lot of issues. Earlier, I made a video about the issue where your hands will fall behind and how to fix it with predicting where the controller is going to be. Um, Now, I want to talk a little bit about how the head works, because if you follow some videos online or tutorials on how to get your a head to physically exist, to get a collider on the head, they're gonna you're gonna have problems with the head being able to push through objects if you run fast enough, or there's various issues with it. You can't slide along the wall, whatnot. Um, Now, what a lot of VR games do to avoid this issue altogether is they make the body collider part of the head. So, for example, say I walk up to this table here. In other VR games, what would happen is you get about this close right here, and then you'd stop. And you couldn't go any further. You couldn't lean your head forward like that. If you leaned your head forward, it would just push you back. So you wouldn't be able to lean over a table. Like, if I wanted to grab this shirt, this is as close as I would get, and then I would just have to manually reach to grab the shirt. I don't like that. I like having my body be the body collider and my head being the head collider. I like being able to, naturally lean over a table like you would in real life. If you wanted to grab something, you'd lean over and grab it. Not only that, like your head just naturally is a little bit in front of your body. So having your head be the body collider, this is about as close as you can get in other VR games to a table, and it's weird, and you don't need to have it like that. You should be able to walk up to a table and lean over a little bit because that's naturally how this stuff works. So, there's a couple different methods to do this. A lot of the physics-based ones you'll see online will just put a sphere collider on the head, and then it's attached to the body through a joint. And then what happens is you try to move your head forward, and it would push your body back. And that works, especially at low speeds. It's fantastic. It works. But you can't run along a wall like that. And if you're moving at high speeds, your camera would actually bounce through the wall. Now you can see that even I'm moving at high speeds, camera doesn't clip through a wall, and I can run along a wall and not get stuck to it. So these are the two main things that you want your head collider to be able to do both those things. And I could not find anything online of how to achieve both of them. So I put some brain work in and found a method, and I'm going to share it with you. So basically, there's two colliders. Let's just get into the engine, and I'll show you. But what you need to know, the important thing you need to know, is that, right, you even at high speeds, you still won't clip through, and it allows you to slide along a wall. Like a lot of other methods where, they're raycasting to check a wall, and then it pushes you back, that actually kind of stops your movement. So if I'm moving like this, and I hit the wall, see how I just continue to slide along the wall? On a lot of other methods, you would do that, and it would stop your movement and push you away. And then you move forward again, and it would stop your movement and push you away. So I just don't like that. And also the same with the physical option where you're using a joint to push the head. Even if you discount the springiness that you can push your head through, when you're walking along a wall, it's kind of the same thing. You sort of bounce off of it, and you bounce off of it, and you bounce off of it, and it's not real. The point of VR is it should feel natural. It should feel real, right? If you're walking naturally, you bump into a wall or something, you're not going to continue to push into a wall. But in a game, we don't feel it, and we're controlling with a joystick. We're not moving our feet, so we just want it to the game to understand that we intend to move along the wall, not actually walking into the wall. And so that's how this kind of effect can be achieved. Let's get into the editor and talk about it. Okay, once again, I am on an ultra wide, so I need to manually tell it to go left, center, right. So if I'm talking about something that's off screen, I do apologize. I'm not very good at controlling this and keeping track of where the camera is. So my VR pawn, this is my character, and there is no head collider at the moment for the VR pawn. So you'll see, well there is. This is just, let me back up a little bit. The body collider, if it's on the root, will slide along objects like it would in any game, like you would expect it to. And so in order for our head to do the same thing, we need a collider that's on the root object, that's the sphere collider here, that follows where the head is, so that we get that sort of frame-by-frame sliding motion. Now, if you just stick a sphere collider on your root, and then like every frame set its center position to wherever the HMD is, it won't work, right? Because it's just setting the position of the sphere. There's no way to, let me go here. This sphere collider right here, right? The only control we have is the center. I can't, you know, do a move or like a casting movement or like a rigid body move cast thing, or like a ray cast type thing. I can't sphere cast to this sphere collider because all we have is a center position. It's just a collider. We can't really sphere cast this. So what we're doing is we're having two colliders. Now the other collider doesn't exist yet, and there's a reason for that. It can't be a child or even on the root of this VR pawn. It has to be its own game object that doesn't have a parent. So if I go to my pawn here, I've got this head physics object. This gets spawned into the world by the player, and then the player takes control of it and starts moving it. And this head physics is very simple. It has a sphere collider that has the same radius as the one that's on the body. That's important. They have to have the exact same radius. 0.22 works for me, but that's entirely up to you in your game. You might want it closer, you might want it farther away. And then also you need a rigid body on it and not kinematic. You don't want it to be kinematic. So collision detection, you can you leave it as discrete because we aren't actually using it the way you think we're using it. We'll talk about that when we get into code, but you're not using the Unity physics to detect collisions with this. We're going to use it. We're using this in script to detect collisions, and then interpolate. We don't need the interpolation either. Same reason. We're doing our own collision detection with this. Obviously, freeze the rotations. Positions do not freeze. Okay, let's get into the code for this. Open up my player. Oops. There we go. All right. Under my IK targets, these are the hands, hand. Here we go, head. Okay, so what we need to do is we're going to check if there's a clear path between where that head-mounted display was the last frame and where we predict it will be by the time the game renders a new frame. Now, the reason we have to do this, we have to predict where the HMD is going to be, because if we go back into the engine and we look at our main camera, right here, it's got a tracked, it's got a tracked pose driver. This updates, see, update type, update end before render, meaning the HMD position is going to be refreshed right before a frame gets rendered. Guaranteed fixed update is out of date. The position that the fixed update loop has for this camera is incorrect. It is old. So we have to predict where we think the camera will be once the render happens. So that's the point. A lot of this code is here to help us predict. So we're going to get, and we're working in velocities, just like if you watch my laggy hands video. It's the same thing for this. We're getting the velocity of the VR camera based on where it was in the last frame, and then divided by delta time. And then we get a smoothed velocity where we're lerping between the last frame's smooth velocity and the raw velocity by 0.3. Now the hands, it was 0.1, but that has a lot of, like, it's a little laggy. In fact, I might turn this up to 0.5. We want this to be really responsive. So with the hands, you want it to be very smooth. I had 0.1 with the hands. You want very, very smooth reaction with the hands because you're getting visual feedback every single frame with the hands, so those have to be smooth. The head, this is an invisible collider, so we just want this to be accurate. We don't want this to be falling behind and be, lagging with the interpolation or anything. This needs to be accurate, but we still need to smooth it a little bit or we'll get some serious jank. Let's see, and then our predicted position is going to be the camera's position plus the smooth velocity times time.delta time. So we're just telling it, you're moving in this direction, predict that by the time the render happens, it's a little bit more in that direction. Let's see, desired HMD move. So this is, we're figuring out the location that we want the, hold on. Okay, so yeah, this is what's going to be used for the sweep test. We're getting the direction that the HMD is moving, which is the predicted position minus the current position of the head collider. Not the one on the body, the free-floating one. And so now we're going to call an if statement, and we're going to do a sweep test on this. So we're going to take our head physics rigid body, we're going to sweep test it from the direction is this predicted velocity direction, this desired HMD move. In that direction, we're going to out the raycast hit info, and then the distance is desired HMD move dot magnitude. So we're going to point in the direction that the camera's moving, that we expect it to move, and we're going to sweep test this collider. Now, if there is a collision detected, this loop will run. So we get an adjusted position, vector3 adjusted position equals head physics transform dot position. So the current position of the head where the collision was detected, like as far forward as you can go. So if for example, the HMD went through a wall, this dot position right here, we're figuring out like how close can we get to the wall. Like what's the furthest this collider can move before it enters the other collider. So that's the math we're doing here. So we're getting the head physics transform dot position where it currently is, plus the desired move direction times hit info distance. So the distance between where it is now and where the collision happened. We're going to go ahead and get that position in world space. Now I had this 0.9 on there because I thought, maybe moving to that exact position might cause an issue where I was sticking to the wall. It didn't, so I don't use it. I just commented out. I used the exact point where the collision happened. So move the head physics to the point of impact. So head physics, rigid body. Again, we're doing a move position. You never do a set position on a physics collider like that. We're moving our head collider directly to the position where the collision happened. Now keep in mind, this isn't the point where the impact happened. This is the point on the sphere, like the center of the sphere's origin, where an impact happened. So we're moving it to the point where it's just touching the wall, or whatever we collided with. And now we need to offset the VR origin to keep the camera out of the wall. So we're pushing the virtual space that the virtual room that the character is in, we're going to push that back. So for example, if there's a wall 5 centimeters in front of us and the head-mounted display moved 10 centimeters, right? We want the HMD to stop at 5 centimeters as soon as it hits the wall. But we know there's 5 more centimeters of movement because obviously there's no wall in the real world and the HMD kept moving. So we're going to push the entire virtual room back 5 centimeters so that the head-mounted display stays in the exact same place in the game world, but the player can still physically move. It prevents us from going through a wall, and everything should work correctly. So we're going to offset the origin of the VR character. Now this shouldn't affect the body, it only affects the location of the head-mounted display and the controllers. It's moving all of that. It's offsetting all of that so that the player doesn't move through a wall. Now if there was no collision, then we just moved to the position that we sweeped to. So for example, we sweep from one frame to the next frame and there was no collision, just go ahead and move it, everything continues as normal. Now after we've done that, we've either had our collision and we've offset, or we've not had a collision and we don't offset, then we need to update the second collider. The second collider is the one attached to the character's body. This is the one that's going to allow us to slide on a wall. So now that we have a safe location that we know for sure is not clipping into a wall, we move the sphere that's attached to the body to that exact location. That way, during the next fixed update, if the character's moving, it can use that collider to slide along the wall and give us the sort of normal full body interactions that we're expecting from other games, like a third-person shooter or something, right? You're expecting to be able to slide along a wall, not get stuck in it. So that's what this second collider's doing. The head, I call this the hard collider. The center position is going to be transformed inverse transform point. So what this is going to do is taking this predicted head position, right, the position where we know that that is safe, the safe position. It either like stopped short of getting to a wall, or there was no collision, and so it's just a safe place. We're moving this body collider, the sphere on the body collider, to that point. And then inverse transform point just means we're giving it a world position, and we're getting that position in local space of whatever the script's attached to, which is the character's body. So get the local space for this, and then set that dot center of that sphere collider to that location. And then our VR camera last position equals VR camera dot position. We need that for the next frame so that we can continue to predict where this is going. And that's it. So really, you've just got 2 colliders that work together. The one attached to the body which is just like the body one. It gives you the same type of reactions that your body collider gives you, is also doing it for your head. But the head, we have to update every frame, and it can only move it to a safe location. Because if you don't have that prediction, what happens is your HMD, you'll push it into a wall, and then that sphere collider will just go into the wall. It won't detect a collision because it didn't sweep to that location. And we can't sweep to that location with the character's body because it will also sweep the capsule, and we don't want that. We only want the head to sweep. So we have to have two colliders, one for the head that does the sweeping, and one for the body that does the sliding along walls. All right. If you have any questions, put them in the comments. Again, I'm not a professional, but I will do my best to help you. I'm a pure hobbyist, but I spend a lot of time figuring this shit out. Nobody else should have to take the time to figure this shit out. So if you have any issues, any questions, let me know in the comments.